Graph interpretation day 2 notes. To start this one off, I'm going to recommend that you actually pause the video and try numbers 1 through 4. And then we'll come back together when you're ready and you can restart the video. We'll go through it together. So one of the things that's important is to know what you're looking at. And in this particular graph, we're looking at f prime. And so you want to start to train your brain to recognize what f prime is telling you differently than if you were looking at f. For example, the extrema of f prime are going to be points of inflection for f, because that's when the slope of f prime would change from positive to negative. So that's where the second derivative would change signs, would be at these extrema, including if there were sharp turns at the extrema. Wherever we cross the x-axis or t-axis, in this case it's x, will be a relative extrema. If we cross from positive to negative, then we have a relative max. And if we cross from negative to positive, we'd have a relative min. If we touch the x-axis but don't cross, it's a critical value but not a relative extrema. So in this particular diagram, we actually don't have any relative min. And the directions here do ask us to explain, and the reason why is because f prime of x never changes signs from negative to positive. We change from positive to negative, which would be a relative max, but we never change signs from negative to positive in the interval shown. And the x-coordinate for any relative max would be at 1. And that's because our first derivative graph, and you know what, these could be improved by saying relative minima of f. All of these are of f. But f prime of x on number 2 changes at x equals 1. F prime of x changes signs from positive to negative at that value. And so that's going to be a relative max. Points of inflection for f will be where the second derivative changes signs. Well, graphically, that would be where the slope of the first derivative changes from positive to negative, or the slope of the first derivative changes from negative to positive. Basically, we could make that pretty straightforward by saying approximately, I don't know exactly. I'm going to say that's around 0.5. I could be a little off, and I'll say this is around maybe 1.5. And really, that's because where f prime of x has extrema is where f double prime of x changes signs. And that's where what we're looking for a point of inflection is the second derivative to change signs. Next, we want to know for what interval or intervals is f concave down. Well, really what we're looking for is for the first derivative, for the second derivative to be less than 0. Well, this is the graph of the first derivative, not the second derivative. So remember that the second derivative is the slope of the first derivative. So I would like the first derivative to have a negative slope, which would mean the first derivative needs to be decreasing. And so looking at the graph, where's the first derivative going downhill or decreasing? It's a little bit hard to tell exactly. We're going to do some estimating. But it looks like x is going to go from around 0.5 to around 1.5. On the other parts of this f prime graph, f prime has a positive slope. F prime is increasing, which tells us the second derivative is positive, and f would be concave up. So take a look at number 5, pause the video, try it first, and then restart the video when you're ready to go over it. Again, we're looking at a graph of f prime. And while looking at this graph, I want to be careful to look at things correctly through the lens, okay? What we're told is that the line tangent to the graph of f prime at x equals 0 is vertical. Okay, so we have a vertical tangent line right here for f prime, not for f. And f prime is not differentiable at x equals 2. Some kids might describe this as a sharp turn. Same idea. We could call this a cusp. Is probably more common for people to describe it, but that same idea of like a sharp turn, cusp. We have a spot where the first derivative is undefined, or is not differentiable right there. So then the second derivative is undefined. The first derivative cannot have a derivative taken there. That's what this means. This means the second derivative is undefined at 2. So which of the statements below are not true? Choose all that apply. First one says the derivative exists at 2. Remember, this is a derivative graph. This is the graph of f prime. If I go to 2, there is a defined value. This is a true statement. The first derivative does exist at 2. I don't know. What is that output height? I have no idea. I'll just call it A. Maybe it's 3. I have no idea. We don't have any type of scale there. But it's a defined point. It's not an open circle. Now, many people choose this as a false statement because they will looking at this statement. But this means that the first derivative cannot have a derivative taken. What this means is that the second derivative at 2 does not exist. Not the first derivative. That's tricky. All right, B. F is increasing on the interval from 2 to 4. Well, when F is increasing, it has a positive slope. That would mean the second derivative should be bigger than 0 or above the x-axis. So let's take a look. From 2 to 4, I am always above the x-axis. This is another true statement. I'm not looking for the true statements. I want the false statements. So I'm not going to choose that. Part C. The graph of f has a point of inflection at x equals 2. Well, when you're looking at a derivative graph, the points of inflection are going to be where f prime has an extrema. And that's because wherever f prime has an extrema would be where the slope of f prime, which would be f double prime, changes signs. We were going either from uphill to downhill or vice versa. And so this one is also true. We have an extrema of f prime. That would tell us that the second derivative has a sign change and f has a point of inflection. D. The graph of f has a point of inflection at x is equal to 0. Well, what I'm looking for here is I'm looking for a point of inflection again to have an extrema on f prime. That's not true. That is not true. I do not actually see a sign change for the second derivative. The second derivative would be the slope of the first derivative. I'm going uphill, uphill. For that, right around there in that region, I do not have a sign change for the second derivative. The visual way a second derivative will look on a first derivative graph, if there's a sign change, is there'll be an extrema. This is the one we want. Let's just verify that with E. F has a local max. Well, if there's a local extrema for F, then F prime should change signs from positive to negative. So let's just see if that's happening. A local max, it should change signs from positive to negative. Let's see, this changes from negative to positive. Oh, this is choose all that apply, so we can have more than one answer. I'm glad we looked at the directions because this one is false. This does not have a local max. This one has a local min because f prime changes signs from negative to positive. And so this is another false statement. So both D and E are the false statements, and so those are the ones I want to choose. We've worked a little bit with sketching graphs of derivatives. So why don't you give these a shot? It's good that we're going to practice it a little bit more, but take the video, pause it, try both 6 and 7, and then when you're ready, restart the video and we will compare together what these graphs of derivatives should look like on this problem. Okay, so to take a graph here, when we're looking at the graph of the first derivative and we're given a graph of f, what we're working on is finding the slope. Whatever the slope is will be the height of the first derivative. I find it easiest to look for places where the slope would equal 0. That gives me kind of a little starting point. So my derivative will equal 0 when I have those relative extrema. And notice that my relative max here, I'm changing from an uphill graph to a downhill graph. This means the slope of f changes from positive to negative. This means f prime changes from positive to negative. So I need to be going from above to below. Now, right here at the minimum, my slope is changing of f from going downhill. I have a negative slope. F is going downhill. The slope of f is negative and then changes to a positive slope. So this means that f prime is changing from negative, where I'm going downhill on f, to positive for f prime when f is going uphill. So I need to be able to change at this 0 on the derivative graph from a negative to a positive. So my graph looks something like that. How deep does this little valley go right here? I don't know. It doesn't really matter. What I do know is somewhere my concavity changed, and where that concavity appears to change should look like an extrema on the f prime graph. A couple other things to think about. This appears to be a cubic function. We could find out a little bit better if we really spent some time on it in terms of what is the leading coefficient, et cetera, blah, blah, blah. Well, then remember the power rule would give us then a quadratic function. So I should have a quadratic here for f prime. It's a little risky doing this just because sometimes you don't have enough of a graph to know if it's really a cubic or not. So you really do want to work more with, are the slopes positive or negative? Number 7, I have some straight segments for parts of this. And where there's straight segments, I can actually calculate slope by using rise over run. So if I just maybe pick a couple places where this appears to go through, nice and clean. It looks like this is down 4 over 2 or down 2 over 1. For this section of the graph, the slope is negative 2. And so my slope is going to be negative 2. Everything to the left of the 0. Now at 0, I have a sharp turn, so the derivative will be undefined there. I'm going to now work with another straight segment, and the slope here is up 2 over 1. So now the slope is positive 2, and at the sharp turn it was undefined, and at this discontinuity it'll also be undefined. I'm now going to work with the quadratic portion of a quadratic. Where I have the relative extrema, the derivative has a slope of 0, and it's just random that happens to be at the same height here. The answer for the derivative is 0 here because of the extrema, not because the height of the red curve was 0. And because this is a min, I went from a negative slope to a positive slope. So I don't exactly know how deep down this goes, but I do know I need to be below the x-axis and then above for my slope. And I should have an open circle. You might wonder why I made this section here linear. That's because this appears to be part of a quadratic. And kind of with the same reasoning as before, if part of my graph is a quadratic, when I take the derivative and use the power rule, I'd end up with something linear from there.